In this webcast, Joachim Beck of Linaro Security Working Group talks about the Meltdown and Spectre vulnerabilities with respect to secure domains like TrustZone.
This is actually based on a deck that I've sent out to various people interested in what we have been doing and so on. And the first part of it is just to give it a background to be able to understand a little bit better what Meltdown and Spectre is about. I think that makes things a little bit easier when we're talking about it later on. So the first thing is speculative execution. And the thing is that the CPU will do things that, if you read the code, it's not really supposed to be happening. So in this simple example I've put together here, you can see it's just a string, and you have some limits, and you can take some arguments to it. So which basically just prints the string. That's it. So nothing fancy happens here. If I send different size to the argument here, I of course get different parts of the string printed. But if I take a too big string, nothing really happens. I mean, this if case we have here where pos is less than limit. If I have my argument is greater than that, it will just not do anything. So that's all fine. But when it comes to this part with speculative execution, things are actually still happening in the CPU itself. So under some conditions, it could actually be that the CPU will continue and read the buffer, and you have this pos here that is being used. So you can imagine what happens here if you actually send a number that is greater than limits. Then this speculation could start to look into the buffer out of bounds in this case. So this is kind of the basis to Meltdown, but we will look a little bit more into it later on. So speculative execution is the first one. The next one is, and these are kind of related also. I mean, they're kind of make use of each other and so on. But the branch predictor is, just as the name says, it will predict where to go here next when you have branches. And that could be both conditional branches, indirect branches, and so on. In this case, with the branch target buffers, it's basically a big list you have. You can see it as a map from PCs to indirect addresses. And I will come to this also later on when we talk about variants to this one of the Spectre exploits. But you should just think about this. I mean, there are some CPU features that will try to make some good guesses of what to do here next. And based on those good guesses, the speculative execution will take over and run that. The third thing we have is the out-of-order execution. So it could very well be, I mean, if you see the pipeline on a CPU, you know it kind of reads instruction by instruction, but it's also optimized so it could do things in non-linear fashion. I mean, it could basically, as in this example here, you have the move instruction. Let's say that takes a long time to complete. So instead of just stalling the pipeline and wait for it to finish to bring in the information to memory, it could actually continue and running the other two instructions and finalize them before doing the first instruction. So that's the out-of-order execution. And this is one of the key things about the meltdown part of the attacks. The fourth thing here now before going into the attacks is I just want to talk a little bit about side channel attacks. So the first bullet here says it quite well. I mean, you are able to observe some kind of behavior and patterns that you're not really supposed to be able to see. There are at least a couple of examples here. Timing attack. There is a schoolbook example that you quite often see that if you're, for example, using mem compare when you are comparing a password, you can basically measure the time. I mean, the mem compare itself returns as soon as something doesn't match. So you can imagine in that case that you can brute force it quite easily by if you have the correct string for a password, it will take longer time for memcompare to return than if you have an incorrect password. So that's the schoolbook example that people usually refer to with this kind of attack. You can do similar attacks with measuring power. So by looking at the power consumption, you can figure out what's going on actually in the code, and there has been a lot of embedded devices that has been totally compromised because of this. I mean, it's leaking information. For Spectre and Meltdown, it's a cache timing attack that they are using. They mention a couple of them, and I've listed 2 of them here: flush and reload and prime and probe. So with the flush and reload attack, you basically empty the cache entirely, and then you call the victim itself, and it starts to do its work. And while it's doing its work, it will actually put information back into the cache again. And when you are returning back from the victim, you can just probe it and see. You basically loop through all the cache lines in the cache, and if you have a cache hit, well, then you know that that was something that has been touched by the victim. And in this case, we're talking about shared memory. Prime and probe is almost the same, but kind of the opposite way. Here, this is something that you can use when you don't have the shared memory. And in this case, you, as an attacker, fill the cache instead entirely before jumping over to the victim. So when the victim has been running the code, something has changed in the cache, and that is something that you can notify or figure out as attacker when you are looking at the cache again, so to say. I mean, if you get a cache miss, then you know that someone has changed something in the cache. So if you read the white papers now about Spectre and Meltdown, you will see this being mentioned a couple of times. So, Meltdown, Spectre, mayhem. So the first day, I think I took all these pictures the 4th last week, so it was all over the news. And it's quite serious. I mean, it's otherwise there wouldn't be all this information about it and so on, and it's been kept secret from a lot of people and so on also. This is the people, so it's basically a mix of people from university and some security firms and Google and so on. If we start by the first one, variant 1, so this is Spectre has 2 kind of variants here, and the first one, bounce check bypass. This is basically what I introduced to you with this speculative execution here. So what happens is that you get some kind of parameter, untrusted parameter, and under certain conditions it could be that this parameter leads to you loading memory. In the paper they explain it as 2 stages, and I have a next slide I think is about this also. But the ideas are again that you will force the speculative execution to do instructions, which in turn will put things in the cache that are not supposed to, well, they are supposed to be there, but from security point of view, it's not really good because you're leaking information here as some kind of covert channel. And if you're interested about a little bit more about how people are actually looking at caches and so on, please have a look at this link here. You can just go to Google and search Armageddon and you will find this. And this is actually some of the people on this YouTube clip is one of the people mentioned on the previous slide of the findings of Spectre and Meltdown. Down to the left side, this is the code that is coming from ARM as trying to show how this works, but I also copied in the shorter one here on the right side from the Spectre white paper instead. So, but it's basically what I just said. So if we have this image on the right side here, if x less than array 1 size. So x here is the untrusted parameter. And again, as we talked about speculative execution, branch predictor, and so on, what happens here is that if you have a number greater than the array 1 size, it could actually be that the speculative execution go in here and you can see the index here of array 1, which will actually get a value from array 2 that you're not supposed to access. And you will not really see it. I mean, as a user, you can't really see it. The only thing we really see, the only thing we really see is what end up in the cache, because these kind of intermediate states that you have, they will just be discarded. The CPU will just throw them away. So everything is fine in that sense. It's just that things are leaking out to the cache. That's the main problem here. And Spectre attacks, Meltdown, and so on are various ways to do this in a smart way, so you can actually get information that you're not supposed to get. I mean, over different privilege levels and so on. The thing with this variant 1 here is that in theory it could be used across boundaries. I mean, from privilege levels, user space to kernel, you can go from non-secure to secure side and so on. I think it's pretty hard to do this kind of exploit in reality, but it's, of course, I mean, it's proven that it's been done in the white papers, and they have demonstration and so on. So the white paper mentions the packet filter code and also JIT, I think, and that's, I guess that's what they have been using when they have exploiting this from user space to kernel. And the thing with this variant 1 here, I mean, the mitigation we have heard from ARM, for example, is that you are supposed to put barriers in the code. There is one existing barrier called CCell, and there is one new barrier called CSDB that has been introduced. The tool chains are being patched right now. I heard about GCC and LLVM. So I guess we will get tools to help us find issues, and eventually, I mean, well, I'm not sure about this, but eventually in the future it could even be that it kind of finds things and patch it for you automatically. But the thing that is a little bit worse about this one is that there's no really good fix and forgets for this one, since even though if we add our fixes now and let's say we find all the barriers that we need to add, we still need to keep track of this in the future. And I mean, relook at our code and see, could we have introduced some kind of issues again, and so on. Different things are affected by this. For example, ARM is, if you go to their page, you can see that most of their processor architectures are affected by Spectre, this variant 1 and variant 2. But on the other hand, if you look at Meltdown, which is the most dangerous one and most easy to exploit, there's basically no ARM processor that is susceptible to that one. It's the A75 that I think that is listed on their page, and that's not really even out yet. So from ARM, Meltdown is not a big deal. Spectre, yeah, it could be an issue, but at the same time, both attacks for Spectre are considered to be really hard to exploit. So I don't think it's the end of the world, even though the issues are serious. So variant 2. This was what I talked about, this branch target buffers, the mappings between program counters and indirect branches. So basically you have a big list with addresses which consist of, you can see it as a history. I mean, if it has passed some kind of branch in the past in the code, it takes some note of was the branch taken or was it not taken, and then it records it. And next time it will enter the same kind of address, it knows where to start to predict and do the speculative execution. So what this issue here about is that you can train the branch predictor. Basically, you can, this history with decisions of where to go can be trained to always be taken, for example, or always not be taken, and so on. And since these branch target buffers are shared across exception levels. It means that in theory you could actually train it to do some speculative execution in a way that you wanted to do it. And again, that will affect the cache, and the same story again. The cache can leak in the information that you're looking for and so on. So this is a little bit interesting attack in that sense. This is basically what I just said. And yeah, this is also one of the 3 issues that is thought to be hard to exploit, but still doable. But again, this is also across different privileged domains and so on. I mean, if you're running user space Linux on core 1 and you go down to secure world TrustZone on the same core, well, if you are able to actually train the branch predictor and find a place where you can use this, then in theory you could be able to exploit this here. So then let's jump into the third one, which has been the one that there has been most discussions about and performance issues and so on. The meltdown. I think most of the people know, at least people working with Linux, they know that user space processes, they share the memory mappings. You have all the memory mappings both for the user space process itself and the kernel. And the mappings for kernel is always there, so to say, and that's a performance thing. Because if you have the mappings all the time, then you don't need to reload everything again and so on. So this is a performance issue that you have that. But what happens here is that when you're running a program in user space and go down to the kernel, if you try to access kernel memory, which you're not supposed to do from user space process, then you will get an exception and a trap. And that trap in turn will, for you as a user, you will just see that you get some kind of error message back, or it will terminate your process. That seems fine. I mean, there are protections and so on, so user space shouldn't be able to do these kind of things. But due to out-of-order execution, what happens is actually that before this trap actually returns, some information are executed, again, by the speculative execution. So if you have a syscall or something that is kind of exploitable here in this case, you once again have the speculative execution, which could potentially access kernel memory, and again, the same story, it will end up in the cache. So this is what all this is about. And the mitigation here, that's, well, not rushed together, but yeah, some kind of rush at least, from both, I mean, Mac, Linux, Windows, everything, is that you're no longer going to share the entire kernel with user space. You will just have small parts of kernel mapped when you're running a user space, so you can do interrupts and so on. And with this fix, you can't really get access to the kernel memory. So the issue is kind of still there, but it's hidden. You can't really exploit it anymore with this kernel page table isolation, as they call it in Linux. So, and then the mitigations for this variant 3, as I said, this kernel mapping. This is the big deal. I mean, in the news, you have seen all this discussions about performance and so on. So since you no longer have the kernel mapped in all the time, you basically need to reload it every time when you're going down from user space to kernel. So in the past, when you went to kernel, it was already there, everything. Now you need to look up the kernel mappings again, and that takes time. And that's where you get the performance hit in this case. So depending on how often you are doing this, the amount of syscall basically affects how much performance hit you will get in this case. So I think that was a big summary of the 3 different issues. So I have put together a couple of possible attacks here for at least for Opti. This is from a TrustZone point of view here. So here I'm talking about the gadget. The gadget is something that you can see it as a piece of code that runs some kind of instruction in a sequence that makes this exploitable. When you hear about return-oriented programming, that is something ROP that you see often in when people are doing, attacks. This is the same kind of gadgets we're talking about. You need to find a certain piece of code in the binary that matches this, that you can use as some kind of trampoline to go further into the code and so on. And I think this is one of the things that make this really hard to attack in practice, because finding that could be quite tricky. And it could also be worth to mention that from TrustZone point of view, even though that also is affected, I think it's harder to actually exploit this in reality than that it is on Linux. And the main reason for that is that when you're running Linux, Windows, Mac, anyone can write a program. You can't really stop anyone from doing that. But when you're running TrustZone, it's so far always the SoC or the OEM that control what trust applications can run on secure side. So they are signed. So if you try to put something else and load it, it will just, the team will refuse to run them. So that makes it even harder to exploit this. Here I'm actually mentioning some patches and so on. Since we have this, as I initially mentioned, we are working with this open source project, Opti, which is a TrustZone environment. We are affected by this, so we are trying to patch it now. So here are some links to different pull requests on GitHub that we have. Some of them has been merged already, some of them are being reviewed and so on. And again, Meltdown, we're kind of repeating a little bit here, but now since we have jumped over from Linux side to TrustZone side instead. But yeah, same situation here. I mean, inferior or someone from a trust application could actually do the same kind of attack here as been described from user space in Linux to Linux kernel. So trust application could do the same thing, trap, execute out of order, get the things in the cache, and you can figure it out and so on. So the mitigations we have done here is basically the same as being done on Linux kernel. So we keep the amount of kernel that's being mapped to a minimum in this case. Performance-wise, I mean, since people are interested, this is what one of my colleagues here figured out when he was running it after patching it. So we can't really see any difference on secure side in our test cases when running it with the fixes and without the fixes. So that's good news for us. So I think this was the presentation as such and an introduction.
Please visit opti.org to keep up with the latest advisories. There are more details in Joachim's blog post on linaro.org. And for affected processor architectures, please see the update from ARM. Here are some links to relevant resources. Linaro Developer Services has significant experience securing ARM systems, including secure boot, working with TrustZone, porting Opti, and working with trusted applications. Linaro delivers engineering effort to develop key technologies for the ARM ecosystem. Linaro delivers its output to its members, into open source projects, and into the community. Check out our websites and projects which we host or support. For more information, linaro.org and opti.org. Thanks for watching.